Okay, good morning to this and welcome to this 10th lecture of the course Compressible Flow and Gas Dynamics. So in the previous lecture we started flow analysis of the normal shock waves, and if you do remember what we have done, basically we have predicted the properties on the downstream of the shock such as P2, rho 2, T2, etc. as the function of upstream Mach number M1, okay, for a given calorically perfect gas. Also we have predicted the value of M2, okay, and it was found that when my Mach number is greater than 1, that is, we have a supersonic situation. Corresponding to that, on the downstream the flow will become nothing but subsonic, okay. So it means velocity of the flow will decrease. On the other hand, if we see, the pressure was becoming greater than P1 because P2 by P1 ratio was greater than 1, okay, and then T2 was also becoming greater than T1, as well as rho 2 was also becoming greater than rho 1, okay. So this is something which we have done, and one special case also we have tested. When if Mach number is equal to 1, then my downstream Mach number remains the same and all the property ratios will also be remaining the unity. So it means properties will not vary. So this type of situation is something which is a special case of infinitely weak shock wave, is called as nothing but a Mach wave, okay. So this is what we have done. Now can you tell me what was the ratio of P2 by P1? In the previous lecture I have given you the ratio of P2 by P1. 1 plus gamma M1 square multiplied by 2 into 2 into M1 square minus 1. So this is like this, okay. Gamma plus 1 into M1 square, okay. So say this was our value of P2 by P1, okay. So now what you can do, you can actually test the applicability of this. Is it correct or something else was also there? Okay. So what you can do now, you can actually try to determine this for a limiting case of M1 approaches to infinity, okay. So when M1 approaches to infinity, what will happen to this value? What will happen to P2 by P1? So what you can do, you can divide this complete equation by M1. So if you divide by M1, it will become 1 by M1 square plus, sorry, let's not divide this term, let's divide only the term after this plus sign, okay. So what will happen then? I will get 1 plus, this M1 will go away, 2 times gamma into, here I will get, this outside was M1 square. So let's divide with M1 power 4, okay. So if I divide with M1 power 4, it will become 1 by, or simply you can do M1 square will cancel out. This M1 square is cancelling out, and inside if you divide by M1 square, then it will become 2 gamma times 1 minus 1 by M1 square, and divided by gamma plus 1 by M1 square, okay. In the numerator also we are doing so. So what will happen from here? You will find that this 1 by M1 square will become 0, this will also become 0. So 1 plus 2 gamma will be my ratio of P2 by P1. So how much is gamma for air at standard conditions? So gamma for air at standard conditions is nothing but 1.4. So 1.4 into 2, 2 point plus 1 is, so ratio of P2 by P1 for limiting case will become something like this. Okay, so this is how you can calculate your other ratios as well. Okay, so what I am saying over here, that already I have given you the formulations in the previous lecture for P2 by P1, T2 by T1 and rho 2 by rho 1. Okay, so now a limiting situation can be that we have nothing but a infinite value of upstream Mach number. So if I substitute the infinite value of upstream Mach number, I will be finding that all these ratios will become nothing but the sole function of gamma. So likewise I have calculated P2 by P1, likewise my rho 2 by rho 1 and T2 by T1 will also become sole function of gamma. Okay, and then by considering the value of gamma equal to 1.4 for air at standard conditions, we will be able to determine this ratio in the form of some constant numbers. Okay, so that means that gives us the limiting value corresponding to which maximum rise in density, temperature and pressure can be obtained. Okay, just on the downstream of the shock wave. Is this point clear? Okay, now let's try to see one important aspect, that when we are having shock waves, okay, so what is happening to the entropy? Okay, so we have some situation like this. This is our shock wave, this is point 1 and this is point 2. So how entropy of the flow is actually changing? Okay, entropy change is associated with the shock wave. So can you tell me how I can determine the entropy change for this situation? So if you see, this is nothing but a air, our working substance is air, and if we consider that we have situation of calorically perfect gas, then we have obtained the entropy equation in our review of thermodynamics lecture, where we have written that specific entropy change S2 minus S1 can be written as Cp times ln of T2 by T1 minus P2 by P1. Okay, now do you know the ratio of T2 by T1? Yes, we have calculated previously. So if you substitute over here, then I will get S2 minus S1 equal to Cp ln. Can you tell me what is T2 by T1? What is T2 by T1? One gamma m1 square 2 into m1 square minus 1. Yes, yes. So this will be another bracket, 2 into gamma 2 plus gamma minus 1. Okay, okay. Two plus gamma minus 1 m1 square upon so this is the value of T2 by T1. Then I will be having minus R ln of P2 by P1, and first term over here is nothing but our, I think, P2 by P1. So let me write it again. Okay, so now ultimately what I have done, I have written the entropy change for a process nothing but in the form of upstream Mach number, because gamma is fixed for a particular substance, okay, and that too if we are considering the calorically perfect gas. So gamma is fixed, so it means entire entropy change I have represented in terms of nothing but the Mach number, okay. So now you will be finding over here, that when my Mach number is equal to 1, okay, so corresponding to Mach number equal to 1, as I told you that T2 by T1 and P2 by P1 will be equal to 1. So there will not be any change in pressure ratio and temperature ratio if you do substitute in this equation. So for Mach number of 1, we will be finding that our S2 minus S1 will be 0. Okay. So if you do substitute over here Mach number equal to 1, you will find that S2 minus S1 is equal to 0. However, if my Mach number is greater than 1, then from here we will get S2 minus S1 is greater than 0. And if you do substitute your Mach number is less than 1, then S2 minus S1 over here will become less than 0. Is this point clear? So ultimately we have written our entropy change equation, entropy change of the fluid flow, completely in the form of Mach number. As we have written it completely in the form of Mach number, so what will happen? If I have Mach number equal to 1, entropy change is becoming 0, which is the case of a Mach wave. And then when my Mach number is greater than 1, then S2 minus S1 is becoming greater than 0, and when Mach number is less than 1, then S2 minus S1 is becoming less than 0. Now if I have to particularly write down the generalized energy change, entropy change equation for this situation of given shock wave, I can write S2 minus S1 is equal to integral of del Q by T from 1 to 2 plus integral of delta S generation from 1 to 2. Is this point clear? That is what I can write from the generic entropy equation. Now if you see in this generic entropy equation, particularly for the shock wave, we are not adding any heat, we are not removing any heat from the shock region. Okay, so the process in the shock region is nothing but adiabatic. So properties are changing, but these properties are changing adiabatically. Okay, so that is the reason that what I can do, I can make this del Q by T as 0. If del Q by T is 0, so I can say that whatever entropy change S2 minus S1 I will be having in this situation, that whole will be because of the entropy generation. Okay, so entropy change over here is only because of entropy change across the shock wave is only because of entropy generation. We also know one interesting fact that delta S generation is always greater than equal to 0. Okay, so if delta S generation is always greater than equal to 0, then S2 minus S1 has to be always greater than equal to 0. So it means this third condition which I am getting for Mach number less than 1, S2 minus S1 less than 1, this is something which is not feasible. Okay, so this is interesting to note that mathematically we have understood that when our Mach number is less than 1, then flow is nothing but subsonic. Okay, so when we are having a subsonic flow situation, we are not having presence of any shock wave. So here physically also, by taking the help of entropy equation, okay, and so by taking the help of entropy equation, it means by taking the help of second law of thermodynamics. So from the second law of thermodynamics also we are getting that if my Mach number is less than 1 and if I say shock wave is present in that situation, there I am getting entropy generation term as less than 0, so which is nothing but a non-physical situation. Okay, so it means over here we can see this as nothing but the important application of second law of thermodynamics, which over here is helping us in predicting the flow situation. Okay, so it is telling us that second law of thermodynamics is telling us that if Mach number is less than 1, then Sock relations are not applicable. So it means there is not presence of the Sock wave. Is this point clear? Another interesting fact is over here that we are saying that S2 minus S1, whatever is we are getting over here greater than 0, that is entirely because of the entropy generation. So physically what is happening near the Sock wave? Why it is becoming, why entropy is increasing in a physical situation? Okay, so physically what we can say that, as across the Sock wave I am having, say if this is my Sock wave, just above the Sock wave my pressure is P1, below the Sock wave pressure is P2, which is very large than P1. Similarly here temperature is T1, here it is T2, which is very large than T1, and also in the velocity also we are having the significant drop. Okay, so it means that in this particular Sock wave region what we are having nothing but, because the thickness of the Sock wave region is nearly of the order of 10 to power minus 5 centimeter. So in this very narrow range, property is changing from very small value to a very high value. Okay, so it means here we will be having presence of large gradients. Okay, so here we are having presence of large gradients. So if you are having large gradient of temperature available over here, so it means we will be having presence of conduction effect. If you are having large gradient of velocity present over here, we will be having presence of over here viscous dissipation. If we are having presence of large pressure drop over here, we will be having lack of mechanical equilibrium. Okay, so if we are having the completely the lack of equilibrium in this situation and large gradients are present, it means these are nothing but physically the irreversible situations. Okay, so physically all these are nothing but the irreversible situations. So if these are irreversible situations, then what will happen? In an irreversible situation, we know that we are having generation of the entropy. So are you able to relate this point? So the idea is that as we have the presence of large gradients, so these will lead to all irreversible effects such as thermal conduction, okay, friction, lack of mechanical equilibrium, etc. Okay, now let's try to see one more interesting aspect. So till now it is interesting to note over here, till now we are saying that flow is occurring from point 1 to point 2, and we are saying that P2 pressure is greater than P1. Okay, so can this situation is possible? Can we have flow from low pressure to high pressure? Ultimately what Sock wave is doing, it is actually increasing the pressure. Okay, so if it is increasing the pressure, so do we have over here the compression of the medium, but flow is still from low pressure to high pressure? Is it physically sustainable? Can you tell me from your fundamental understanding of fluid mechanics? See, if you recall, we have defined two important terms. One is static pressure and one is total pressure or stagnant pressure. Okay, so this I am representing with symbol P only, this I am representing with symbol P naught. So for the flow to occur, actually the total pressure should be from high to low. Okay, static pressure can be low to high as well. Is this point clear? So it means this situation is physically possible, but still we don't know the condition of the total pressure or stagnant pressure. So unless or until we are able to predict the total pressure or stagnant pressure over here, we will not be able to determine whether this situation is physically possible or not. Okay, so let us now attempt to determine the stagnant pressure on the upstream and downstream of the shock wave. Is this one clear? So what I will do over here, first let me try to consider what happens to stagnant temperature. Okay, so we know that our energy equation is H1 plus V1 square by 2 equal to H2 plus V2 square by 2. And for a calorically perfect gas, I can write Cp times T1 plus V1 square by 2 Cp times T2 plus V2 square by 2. Okay. Now, can you tell me what is the formula for stagnation temperature? So, what we do in case of stagnant condition? Say, if I am having some temperature T, if I deaccelerate the flow from this condition till my, if velocity is V, till my velocity becomes 0, then corresponding to this what temperature I get, that is called as T naught. Okay, so if I do apply over here the energy equation, and this process we do nothing but in an isentropic fashion. Okay, so in an isentropic manner I have to deaccelerate the flow over here. So over here if I do apply the energy equation, I will get Cp times T naught equal to Cp times T plus V square by 2. So I can say this combined term is nothing but over here Cp times T naught 1, stagnation temperature corresponding to situation 1, and this second term over here is Cp times T naught 2, which is stagnation temperature corresponding to situation 2. For a calorically perfect gas, Cp I can cancel out, and ultimately I will get nothing but T naught 1 equal to T naught 2. Another interesting fact. So stagnation temperature over here is actually not changing, and this is very true. Why? Because we are not adding any heat, we are not removing any heat. Okay, so static temperature can change, but stagnation temperature over here is actually not changing. The reason for no change in stagnation temperature is because in this particular situation what we are doing, we are not adding any heat, and physically we are not removing any heat. So as there is, the process is adiabatic, so in this situation stagnation temperature is remaining the constant, whereas static temperature, because of the changes in flow parameters, is actually changing. Okay, is this point clear? Now let's try to find the next situation. Okay, so next what we have to find? We have to find out the value of stagnation pressures. Is this one clear? So for finding out stagnation pressures, let's consider that this is my shock wave. Say this is my one fluid element over here. Okay, this is one fluid element, and this is another fluid element over here. Now what I have done, say this is at condition 1 and this is at condition 2, that we already have. Now if I isentropically deaccelerate this to situation where my state is becoming 1a till my velocity becomes 0 over here. Similarly, I am isentropically deaccelerating this fluid element such that over here also the velocity becomes 0, and this is my situation, say 2a. Okay, is this one clear? Now ultimately my point 1a and point 2a are nothing but representing the stagnation properties for condition 1 and condition 2. So I can say over here, corresponding to this green fluid element, I will be having temperature as T01 and pressure as P naught 1. Okay, stagnation pressure corresponding to this situation. And here I will be having temperature at T naught 2 and pressure as P naught 2. Okay, is it clear? Now what I am doing, now I am writing entropy change for S2A minus S1A. So S2A minus S1A will become Cp times ln of T naught 2 divided by T naught 1 minus R ln of P naught 2 divided by P naught 1. Okay, so this is something which we will get over here. So now this S2A, because the process from 1 to 1A is isentropic. Similarly, the process from 2 to 2A is isentropic. So for this process I can say that S2A will be equal to S2. So this I can write S2 minus S1 equal to, and we know that for a shock wave T naught 1 equal to T naught 2. Okay. So this first term will get 0. So ultimately I will get minus R ln of P naught 2 divided by P naught 1. Okay. And from here I can get that ln of P naught 2 by P naught 1 is equal to minus of S2 minus S1 by R. Okay, and ultimately I will get that P naught 2 by P naught 1 will be equal to exponential of minus S2 minus S1 by R. Is this point clear? Now if we see this particular equation, here R is constant and it is always positive. Fine. And just now I have explained previously that S2 minus S1 also always has to be greater than equal to 0. Okay. So S2 minus S1 over here is always greater than equal to 0. So from this situation I will get that, P naught 2 by P naught 1 will always be, you tell me, this S2 minus S1 is positive, R is positive, and I am doing exponential of minus of a positive quantity. So it means from P naught 2 to P naught 1 ratio I will be having nothing but a exponential decay. Okay, so it means from here I will get that this will be less than 1 and I will have P naught 2 always P naught 2 always less than P naught 1. Is this one clear? So it means that across the shock wave our stagnation pressure actually decreases. In the downstream of the shock wave we have less total pressure in comparison to its upstream. Okay, so that is the reason that flow is possible. I just now posed you a question, so whether flow is possible or not. So our static pressure P2 is becoming high on the downstream of the shock wave. So P2 is becoming greater than P1, but stagnation pressure or total pressure on the downstream of the shock wave is actually decreasing. So this is the reason that flow is possible from left to right despite the fact that static pressure is decreasing, because flow is governed by the total pressure. Okay, is this point clear? Now one more interesting fact is there. So if you little bit dig historically into the understanding of the shock waves, so you will be finding that whatever equations we derived in today's lecture till now or in the previous lecture, all these equations were actually first proposed, mathematically proposed by William Rankine. Okay, so these equations were proposed by William Rankine. So Rankine's equations were mathematically similar to that of the equations whatever we have seen over here. Okay, and these are proposed somewhere near 1870. Okay, and after William Rankine, one more scientist was there, Hugoniot. He also published a paper after 2 to 3 years of Rankine, and he was not knowing about actually Rankine's work, because that is evident he has not cited that work in his paper, and he also proposed some equations for the shock waves. Okay, and the equations which were proposed, these were nothing but the same set of equations. Okay, however, his analysis was slightly different. He has not taken the help of the Mach number. He tried to determine all the property ratios by just involving the variation of thermodynamic properties, okay, in his particular formulation. So these two people were considered as the pioneers who have actually initially mathematically described the behavior of the shock waves. Okay, mathematical description of the equations, particularly for flows involving normal shock waves. Okay, however, in both of these mathematical formulations, they have not defined the behavior that shock wave, across the shock wave, that it will always lead to compression. Okay, like we have seen just now thermodynamically, that if we consider Mach number less than 1, then we will not be having feasible situation. Okay, so mathematically we were able to find out that if we move from left to right across the shock wave, that is from Mach number greater than 1 situation, okay, then what I am having, my P2 pressure is actually increasing over here. But if I move in the reverse direction, so that is something which mathematically it is open. Okay, so mathematically this condition was open, that in which direction actually flow should proceed while we are having involvement of the shock wave. So after these two scientists, actually Rayleigh has proposed somewhere in 1910 the detailed physical understanding, and he has in his paper explicitly mentioned that shock wave always leads to compression of fluid. So the meaning is always on the downstream of the shock wave we will be having P2 greater than P1. Okay, so this is something that on the downstream of the shock wave pressure will be always greater than P1. That was mathematically open from these two works. So it was finally concluded in in Rayleigh's work that compression of fluid is only possible on the downstream of the shock wave. And once again similar thing happened, that whenever Rayleigh published, within almost the same duration, Taylor has also published the same findings. Okay, so both of their findings were actually matching. So these four people can be considered as William Rankine, then Hugoniot, and Rayleigh and Taylor. These are the persons who are actually initially involved with the development of the shock waves. Okay, and this is the reason that the majority of these shock waves relations are also sometimes known as Rankine-Hugoniot relations. Okay, now let's try to see the approach which Hugoniot has followed to equations or relations to determine the pressure ratio across the shock waves. Okay, so as per his approach, he has just considered the thermodynamics approach without involving Mach number over here, only considered the thermodynamic properties. So from the continuity equation we know that rho 1 v1 equal to rho 2 v2. Okay, so from this equation I can make two conclusions. First is I can say that v1 can be written as v1 equal to rho 2 by rho 1 into v1. Okay, and second conclusion I can make, I can write v2 equal to rho 1 by rho 2 into rho 1 by rho 2 into V1. Okay. So these two things I can write from the continuity equation. Is this one clear? Now we have our one dimensional momentum equation as P1 plus rho 1 V1 square equal to P2 plus rho 2 V2 square. Okay. Now let's replace V2 with this formulation over here. If I replace V2, I will get P1 plus rho 1 V1 square equal to P2 plus rho 2, and in place of V2 I will get rho 1 by rho 2 square into V1 square. Okay. So from this I can write that V1 square times rho 1 minus rho 1 square divided by rho 2 equal to P2 minus P1. Is this one clear? Just I have done some algebraic manipulations, and this will give me what I will get from here. Tell me. V1 square. Okay, and let me consider rho 1 as rho 1 by rho 2 as common. If I consider rho 1 by rho 2 as common, inside I will get rho 2 minus rho 1. This will be equal to P2 minus P1. Okay. So from here I will get that V1 square is equal to P2 minus P1 by multiplied by rho 2 by rho 1. Okay. So this is the formulation for V1 square. Similarly, for V2 square, what I have to do in the momentum equation now, V1 I have to replace in terms of V2. So here I have done a mistake. I should write this as V2. Okay. So here this V1 I have to write in terms of nothing but V2. So if I do so in this momentum equation, then I will get V2 square as P2 minus P1 divided by rho 2 minus rho 1 times rho 1 by rho 2. Okay. Now let's write down the energy equation. So from energy equation we know that H1 plus V1 square by 2 equal to H2 plus V2 square by 2. Okay. So now what I can do, I can basically over here write this H1 as U1 plus P1 by rho 1, because H is equal to U plus pressure by density. Okay, enthalpy is equal to internal energy plus pressure by density, and in place of V1 square by 2 I will write 1 by 2 of P2 minus P1 by rho 2 minus rho 1 into rho 2 by rho 1. Okay, and on the right hand side I will get U2 plus P2 by rho 2 plus half of P2 minus P1 by rho 2 minus rho 1 times rho 1 by rho 2. Okay. So now if you see, this entire equation is nothing but in the form of thermodynamic properties. We have eliminated over here the velocity. Flow velocity we have eliminated. So as we have eliminated the flow velocity, entire equation has become in the form of all thermodynamic properties. So if we do some algebraic manipulations in this equation, ultimately I will find that U2 minus U1 is equal to P1 plus P2 by 2 into specific volume at 2 minus specific volume at 1. Okay, or specific volume at 1 minus specific volume at 2. So this will be the final formulation. So ultimately, if you do some mathematical manipulations, so this is nothing but a simple algebraic equation. So you can do some mathematical manipulations, and you will get a final equation u2 minus u1 equal to p1 plus p2 by 2 into v1 minus v2. Now this is regarded as one of the very important equation. And if you consider, this equation also shows analogy with first law of thermodynamics. Okay, let me explain to you over here. So what does it represent? It represents that u2 minus u1 is equal to P average times delta V. What is P average into delta V? This is our boundary work. So I am getting that change in internal energy of the fluid is nothing but equal to the boundary work. Okay, and here we don't have any heat transfer for the physical situation of shock wave, so it means delta Q will be 0. Okay, because for shock wave we don't have any heat transfer, so delta Q is ultimately 0. So whatever this thermodynamic relation we have derived, this is showing analogy simply with the first law of thermodynamics. So if I simply consider a control volume, and for that control volume if I apply the first law of thermodynamics, I will be able to determine that changes in internal energy are equal to P average into delta. Okay. Another important point is when we do calculate, when we do go with the thermodynamics, we know that for a simple compressible substance, if we have to designate the state of the system, I require two set of independent intensive properties. Okay, so I can say that if I know the pressure and specific volume, because that is something which is involved over here in this equation. So if I know the pressure and specific volume for any situation, then I can predict its internal energy. Can I write it like this from the concepts of thermodynamics? For a simple compressible substance, if we have to predict the other thermodynamic properties, we require at least two independent intensive properties. That is something which we learn from the state postulates. Okay, so that's why what I can do over here, I can write that internal energy can be a function of pressure and specific volume. Okay, so if my internal energy is becoming function of pressure and specific volume in this particular equation, so left hand side will also become function of pressure and specific volume. So ultimately I can say over here, if P2 is the parameter which I want to calculate on the downstream of the shock wave, so I can say that P2 will be function of P1, V1 and V2. Is this one clear? So what I have done, this left hand side, by using the state postulates, I have written simply as function of pressure and specific volume. So this has become function of pressure and specific volume. Now if I have to calculate P2 parameter, that will be dependent upon V1, V2, P1. Because left hand side is also function of P2, V2 and P1. Is this one clear? So from this equation I can take out P2 on the one side and bring all other parameters on the other side. That way I can say that my P2 will become function of P1, V1 and V2. Is this one clear? Is there any doubt, or is this one clear? Okay. So it means that if I know my initial points, and if I have some idea about the flow process, then I can actually predict the value of pressure. Okay, and it is also very much proven from this formulation that what shock wave is doing, shock wave is ultimately leading to increase in the pressure of the fluid, and it means we are having its, and obviously we have also seen increase in density also, so it means its specific volume is decreasing. Okay, so in a shock wave, what is happening basically? if a fluid is moving through the shock wave, its pressure is increasing and its specific volume is decreasing. So it means shock wave is nothing but acting as a compression process. Is this point clear? So you can, in place of a compressor, you can use a shock wave to compress the fluid. Okay. So what I can see over here, but whether this process of compression of this through shock wave is efficient or not, that let's discuss. So if I take a situation on PV diagram that I have, say this is my state 1, okay, and say this is my condition of pressure P2. If I have to go from point 1 to point 2 through an isentropic process, so say this is my S equal to constant. So this process is constant entropy process. So this is an isentropic compression process which mainly occurs in majority of the compressors. Okay. Now through the shock wave, what will happen? We have seen that when flow passes across the shock wave, though its pressure is increasing, but its entropy is also increasing. So it means the compression process through a shock wave is not isentropic. So as it is not isentropic, we will be having some entropy generation. Okay. So it means if in isentropic way, this is my point corresponding to P2 pressure, then corresponding to the shock wave, I have to go to some higher entropy line. Okay. So in place of this, my shock wave process will be something like this. Is this point clear? So this is the compression process through shock wave. Is this one clear? And this type of curve is also known as Hugoniot curve. Okay. Sorry? Process will not be if we have presence of shock wave. Okay. So if you see, just now I have determined the entropy change for a shock wave. So when I have calculated the entropy change for a shock wave, I found that S2 minus S1 is greater than 0 for a shock wave. So for isentropic process, S2 minus S1 has to be equal to 0. Okay. So as in case of a shock wave, my entropy is increasing, so it means it is not an isentropic process. Fine. Up to this point, is it clear or anyone is having any doubt? So it means I am at this point 1, and then if I follow this curve, then I will reach to point number 2. Okay. But still we are not able to exactly find out the path of this curve. Okay. But it has to be above than the isentropic process. That is something which we have actually concluded over here. Okay. Now another interesting fact is that my equation V1 square gives me P2 minus P1 divided by rho 2 minus rho 1 times rho 2 by rho 1. So let's convert all the densities in the form of specific volume. So if I do so, I will get that P2 minus P1 divided by 1 by V2 minus 1 by V1, and here what I will get, V1 by V2. Okay. And this if I do further manipulate, then I will get V1 square equal to P2 minus P1 V1 minus V2 divided by V1 V2 into V1 by V2. Okay. And ultimately this V2 will get cancelled and this will become V1 square. So I will get V1 square by small v1 square is equal to P2 minus P1 by V1 minus V2. If I take minus sign in the denominator, okay, so I will get P2 minus P1 by V2 minus V1 equal to minus of V1 by small v1 square. Is this one clear? Is this equation clear? What is this? P2 minus P1 by V2 minus V1. This is nothing but slope on PV diagram. So slope on PV diagram for Hugoniot curve, it means for the compression process through shock wave is nothing but minus of V1 divided by specific volume at point 1 whole square. So V1 and specific volume at point 1 will be nothing but the constant quantities. So I will get this as a constant negative slope. So it means that if I draw a straight line between point 2 and point 1, then I can say this straight line over here is nothing but slope and its value is minus V1 by V1 whole square. Is it clear up to this point? Now there is one interesting fact that if I calculate so this is nothing but the average slope P2 minus P1 by V2 minus V1. This is the average slope. If I do calculate the instantaneous slope, then instantaneous slope at point 1 will be same for isentropic compression as well as for the shock wave compression. So let's prove that. So what I am going to prove now, if this is my PV diagram, okay, so on this PV diagram, this is one process starting from 1 which is isentropic, and I have this is another process which is also starting from 1, but then it is departing from the shock wave as more and from the isentropic process as more and more compression is taking place, okay, and ultimately I am reaching at point 2. So this is for S equal to constant. So what I want to say that if I do calculate the instantaneous slope at point 1, then for both isentropic as well as the shock wave compression process, these both will be same, okay. So let's try to find this out. So just now I have seen that for shock wave compression P2 minus P1 by V2 minus V1 is equal to minus of V1 by whole square, okay. Now if I impose over here limit of that V2 is approaching to V1, so specific volume of point 2 is approaching to point 1, what I will do, I will reach nothing but corresponding to a fixed point. So if I am reaching to a fixed point, then this average term will become nothing but the derivative. So I can write from here dp by, for limiting situation of V2 approaches to V1, I can write dp by dv equal to minus of V1 by V1 square, because here I don't have any involvement of other parameters. This is a constant quantity, okay. Is this point clear? Then so it means my instantaneous slope at point 1, so this is dp by dv at point 1. So instantaneous slope at point 1 for this shock wave compression process is minus V1 by V1 square. Now if I do calculate the slope for isentropic process, we know that for isentropic process PV power gamma equal to constant, it means P will be equal to C by V gamma. So if I calculate the slope, it means dp by dv, that will become C times minus gamma into V power minus gamma minus 1, okay. Now this C I can replace with PV gamma minus gamma times what I will get from here? P divided by specific volume times minus gamma. Okay, that is what I am getting over here. So I am getting dP by dV is equal to, for isentropic process, is equal to minus gamma P by specific volume, and I am calculating this derivative at nothing but 0.1, so I can write this as P1 and this is cross gamma. In place of P, if I write RT1 by V1, I am getting in the denominator V1 square. Okay, and what do we mean by gamma RT1? Gamma RT1 is nothing but, for a calorically perfect gas, it is speed of sound, A1 square by V1 square. Okay, so now if I take the limiting situation of a one more condition I have to consider over here. If I take a limiting situation of Mach number is equal to 1, then corresponding to that, this A1 I can replace with V1. So it means that when my sonic condition is there, corresponding to sonic condition, I have nothing but the corresponding to sonic condition, the slope of isentropic and shock wave compression at point 1 is nothing but the same. Okay, so this is another important conclusion which we can make over here. Is this point clear? So instantaneous slope at point 1 for this shock wave compression is minus V1 by V1 whole square, and when we are seeing this for slope for nothing but an isentropic process, particularly for Mach number equal to 1, then also I am getting dP by dV1 is equal to minus V1 by V1 square. Okay, so it means that for initial sonic condition, the slope of shock wave compression process and isentropic compression process are nothing but the same. Okay, this is one important conclusion. Another important point is, if this shock wave process can be employed for compression, then why we don't go for shock wave compression? Why we go for isentropic compression process? If you see, in case of isentropic compression process, entropy is not changing. Okay, and here in the shock wave compression process, entropy is increasing. So it means we are investing some amount of energy in changing the entropy also. And mathematically this is clearly evident because this compression process can be equated to that of a control volume approach. Say this is a control volume, some fluid is entering over here. Either you use over here a compressor or a shock wave. At the exit of this, you will be having nothing but your mass leaving at higher pressure and lower specific volume conditions. Okay, so this is nothing but a open system. This is a open system. For an open system, what will happen? For an open system, work done of compression is equal to minus integral of VdP. So VdP integral will give me which area? Area on y-axis. Okay, so from VdP integral I will get this area. So it means that if you see the isentropic compression process and shock wave compression process, which one is consuming more area? Shock wave. Okay, it is taking more area. So it means that the shock wave compression process is not efficient. It is less efficient than the isentropic compression process. Okay, so that's why you will not find in majority of the devices that we are going for shock wave compression process. Okay, all the devices are nothing but tried to be made equivalent to that of isentropic compression process. Okay. Another interesting point is that, so this is my original equation, say equation number 1. Now this original equation number 1 right now is applicable for every fluid, because this is driven from the generalized continuity, momentum and energy equations. Now here if I impose the condition of a calorically perfect gas, then I can write U equal to CVT and PV equal to RT. Okay, so these two conditions can be written for calorically perfect gas. So if I do supply these two conditions, then I will get the first form as P2 by P1 equal to gamma plus 1 by gamma minus 1 into V1 by V2 minus 1 divided by gamma plus 1 by gamma minus 1 minus of V1 by V2. So what I am saying is, whatever equation number 1 I was having, if I do substitute these two things, U if I replace with CV times T and PV I make equal to RT, then I will get this particular final expression for P2 by P1. Okay, and this expression is applicable nothing but for a calorically perfect gas. So you can try the derivation of this by your own, and because this requires only the algebraic manipulations, if there are any doubts, that I will see in the next lecture. Okay, so now I will stop.